When we get into Blackboard, let's go into data sheets. Now, normally diodes, JDEC registered, which is a consortium of manufacturers that finally got together and they said, well, we're going to have to standardize stuff. They called it the Joint Electronic Device Engineering Council, JDEC. And once they register a device in JDEC, it becomes open technology. Not only does the package become open technology, but the specifications for the diode becomes technology. JDEC starts your diodes with one N, meaning it only has one junction, one N, and then they apply a number to it depending on when it was developed. So the bigger the numbers, the newer it is. The first one we're going to look at is called a 914, which is this guy right here. One N. So one N, if you say one N, it means it's a diode. And then the other number don't really mean anything, right? You understand that? So right now, if I could read the number on the side of this thing, if I went up to, Google 1N 914, you'd get 15 data sheets pop up there where you could get them. Don't pay for them; they're free. So you got some sites that sell them. You can go to Jameco Electronics, JAMECO, and type in the part number, and down on the left-hand side there's a little link that says data sheets, and they give these data sheets away all the time for everything they sell. So that's a really good, and also it's a real good mail order place too. If you wanted to start hobbying and buying some of this stuff yourself, they give really, really good prices. We get most of our electronic stuff from Jameco. Jameco, J-A-M-C-O. So this is a typical data sheet for a diode. By the way, the numbers can be written on the side, but they also use color codes. DO is also a JDEC package, and it stands for diode outline, so that's the package. I don't know what LL stands for. But this is what we're looking for. Maximum repetitive reverse voltage. So this is the breakover voltage of the diode. This is how much it can block. Because it's not going to block 100 volts. It's not going to pass. When it's forward bias, it's only going to drop about 7/10, right? You understand? So this guy here can actually block up to 100 volts. So if you put it on AC, that's 100 volts peak. That's not RMS, guys. Y'all understand that? That's 100 volts peak. So you need to know the peak voltage. If you exceed the breakover voltage of a diode, it could be damaged. It don't mean it is going to be damaged. It could be damaged, right? The analogy I look is like the tachometer on a car. If you got a tach on your car, usually it's got a red line on it. If you go over the red line, your engine's not guaranteed to blow up for overspeed. It don't mean it is going to blow up. It's just not. It's not guaranteed anymore, right?
So, whatever it says, V,
V for reverse, repetitive reverse, and I don't know what the M says. Maximum. That's what the M stands for. I can see it now. V would be voltage. R would be reverse. Repetitive, maximum, right? Well, it's a voltage. It's not an RMS voltage. It is a voltage. It is a level of voltage. So it's going to be, and what we don't understand between a effective voltage and a voltage, right? You understand? So yeah, on AC it's going to be peak. If it's DC, we use this voltage right here. If it's AC, what we would do is make sure that the peak voltage that it's trying to block does not exceed the breakover. So I couldn't use this on 120 volts. Because 120 volts, the peak voltage is around 170 volts. We're going to break this guy here on purpose. But what we're going to do is we're going to put a 10 mega ohm resistor in series with it so we don't exceed the reverse current. So then we got IF. This is the forward current average. So this guy here is rated at 200 milliamps. So it's not a big diode, right? It's not really. But it can handle a surge. So less than 1 second, it could handle a pulse. It could handle up to 1 amp. I don't know what the other one means. Oh, I'm sorry. This is 10. Yeah, I know what it means now. So for 10 microseconds, I didn't see the microseconds. All I saw was 1 and 1. So for 1 second, it can handle a pulse of 1 amp. For 1 microsecond, it could handle a pulse up to 4 amps. Now the 1 second becomes important. We'll look at later on. The other one's not. Operating temperature, this guy here could actually get up to 175 degrees centigrade. Power distribution when it's conducting about 500 milliwatts. And that's about it, guys. Let's see what's down here. Oh, this is more in detail. So notice we use 7/10 of a volt, but actually it could be anywhere between what? 620 millivolts all the way up to what? A volt. So if we got it operating at pretty close to its maximum current, the voltage goes up. So we could draw that line, right? You understand that we did before. And notice it's going to be at a slant. But using the second approximation, we don't worry about this. So notice if I use 700 millivolts, we would be 300 millivolts off here, and we'd be 80 millivolts off there. Good gracious, we're still talking about millivolts, right? Well, everything, what we're going to find out is that every solid-state device has a maximum wattage it can dissipate. And, of course, what's going to determine that would be what it's made of, how it's made, and stuff like that. If you exceed the temperature rating of a device, then it's no longer, it's either going to not do what it's supposed to do or it's going to be damaged. So every solid-state device we see is going to have a temperature. Most of these guys, this is pretty standard, guys, when they set up these specifications. Pretty standard, all these. Can y'all see this little old tiny thing right there? TA, what do y'all think TA stands for? Not close. Ambient temperature. Y'all know what the ambient temperature is? Well, it's the surrounding temperature. There might be a lot of difference between the room temperature and the surrounding temperature, right? It's like sometimes you get it's like your car, so it might be 90 degrees outside, you go out there and get in your car, well that would be the ambient temperature in your car, even though the outside is 80 degrees. But what we do realize is that 7/10 of a volt is an approximation. Breakdown voltage, they tested it at this current, so breakdown a minimum of 100 volts, but it could be, what's this one right here? Oh, so if we reverse bias it at this, we should get around 75 volts. So it starts conducting current. When we get up to here, this is where it's going to start really dissipating heat, right? You understand? Reverse current. So this is leakage current, guys. This guy could leak anywhere between what? Nanoamps, which our meter can't measure. You know, very few meters can measure nanoamps. All the way up at 75 volts, this guy here could get up to what? Microamps. So when we say we reverse bias it, it acts like an open switch. It is not an open switch. There is a path through there. Y'all understand? And this would be the leakage current. What else we got? Total capacitance is not going. If you've had AC, you understand that anytime I separate something, two conductors with an insulator, we have a device called a capacitor. So when a diode is reverse biased, it acts like a capacitor. But it's going to be extremely small. So this is only 0.1, 2 picofarads at this megahertz. So this guy could switch pretty fast. That capacitance means that it's going to take a little time between it cutting off between when you reverse bias it and forward bias. So these guys cannot go from conduction to off in no time. That would be like I can go over there on that light switch and switch the light off and on in no time. Can y'all do that? That's impossible, right? But this guy here says I can switch within what? 4 nanoseconds. So this guy switches pretty fast. This is a small signal diode. Some people call this a switching diode. This guy here can operate at extremely high frequencies. The diode we're going to use is a rectifier diode. Use a rectifier diode would have more capacitance, and it's not designed to switch, but it's going to be able to handle more current. So this is a typical data sheet, guys. Y'all got any questions on that? We're going to break this guy over. I mean, we're going to deliberately break it over. So y'all going to use the first lab, depends on how I give them out. One lab we're going to do is you're going to just take diodes and you're going to measure them with your own meter. So y'all need to bring those meter in next class. Right? So we had one guy just left. Jackson left, right? One next to you. Barry just walked outside. He hadn't left his books there. I think he had a phone call. So I'm going to have to talk to him. Y'all know y'all just don't leave my class without letting me know y'all leaving, right? Okay, let's go back and look at a 914. I'm sorry. This right here is pretty standard when you have a series of diodes that carry the same basic number. So this guy here is a 49, we call it a 1N40O, and then there's going to be a number in there for the X. So this is another guy we're going to be using a lot. So let's go and look at this. We should see a lot of the same things, right? Oops, wrong thing, Rich. One in 4000. I hit on the 47. Okay, so here we go. So this is the one. This data sheet actually covers part numbers 1N4001 through 1N4007. Now what varies is this VRMM right here. This is the breakover voltage. So a 4001 can only block what? 50 volts. A 4002 can block 100 volts. A 4003 can block 200 volts. A 4004 could block 400 volts. A 4005 could drop 600 volts. Block. A 4008 could drop 800 volts. And a 4007 could block 1000 volts. What's the far current rated at? Average current this thing can handle? Yeah, it can handle what? 1 amp. This could handle up to 30 amps for one cycle. So we can handle 30 amps, but it can't handle it very long. Huh? Yeah, y'all seen it. This is the guy we're using, by the way. This is the 4001. I don't know. Let's see what this is. This is a 4001. So this guy here is rated at 50 volts. So we wouldn't put this across 120 volts. So here it is right here. Here's my little finger, right? Crushed my thumb cracking pecans, by the way. During the Christmas break. So this is a 4001 right here. Now what you do is we know that the bar is the what? It's the cathode. And then what you do is you just start rolling it around, guys. And we're looking for 1N. So I don't know if y'all can see this now. I can pass it around. It's not going to focus in on it. Oh, it did for a second. 1N, and we just rolled it around and we see 4001. So this is a 1N4001 diode. Very standard. This is a rectifier diode. The rectifier diodes are not designed for high frequency applications. I was working on a TV and a diode went out on it. It was up in the horizontal circuit. The horizontal circuit runs at 15,700 hertz. And I didn't have a diode, so I got old 4001 and stuck it in there. It didn't last long because it was a diode that was not designed to run at high frequency. And sure enough, it burned that sucker up. And Rich learned a lesson. Unfortunately, some of the lessons you learn in electronics is when you mess stuff up. Operating junction temperature is not important. This guy here, what would be the voltage? What would be the forward voltage drop I would measure across this thing? So I'm looking down at electrical characteristics. A maximum of what? 1.1. A minimum of, just don't give us a minimum. An average of what? 0.8, right? 800 millivolts. So that's the average. We're going to use 700 millivolts, but This thing says it averages 800 millivolts. So using the difference between you using 0.8 millivolts and that is not enough to even worry about, right? Y'all understand what we're saying? Maximum reverse current. So this is our leakage current. It could be 50 nanoamps, a minimum of 50 nanoamps, all the way up to 50 microamps. So that's the reverse leakage current. So what we're saying is this guy, it's going to leak, right? You understand, because there's a path through there. But the leakage current is going to be so small, 1 amp forward bias, putting all this voltage across there, 50 microamps reverse bias, and that's if it's operating at 100 degrees centigrade. You know how hot 100 degrees centigrade is, guys? Multiply it by 9/5 and add 32 to it. So we would be very uncomfortable. We would be burning up on that. So this diode can operate pretty hot. This is the diode we're going to use in our power supplies. So when we start making our first power supplies, we're going to use the 1N40 something. We're going to use a 12.6 volt center tap transformer, which gives us a peak voltage of around 17 volts, 17.8 volts. So the 4001 would work fine. Y'all understand that? What about a 4002? It would work fine. What about a 4003? It would work fine. So that means if you come over and say, well, I need a 4001 and I give you a 4007, are you going to be disappointed? No. In fact, it would be better, a lot better than what we need. All this stuff does not vary between these transistors. What varies is the breakover voltage. So on a 12.6 volt center tap transformer, 4001 would work fine. Because like I said, peak voltage is what? What do we calculate? 17? It'd be about 20 volts. This guy here can block 50. Normally we look at double what we want to block for obvious reasons. So this guy right here would work fine. If I was going to run this on Alabama Power though, I'd probably use this guy right here, the 4004. Because that's 170 volts peak, right? You understand? And we double that. And if I did 1,000 volts, if this didn't work out for me, then I'd find another diode because they're all out there, right? Or if I needed to block 2,000 volts, what could I do? Well, I could put two of these guys in series, cathode to anode. And now we'd lose 1.4 volts, but, if I'm dealing with extremely high voltage, 1.4 volts wouldn't be any difference. So normally real high currents, we're going to deal with high voltages anyway, right? So if we hook them in series, it does nothing about the amount of current we can push through because they're in series. So if one of them's conducting 1 amp, the other one's going to be conducting 1 amp, right? You understand that? So what matters, what we get when we start hooking them in series, is these guys right here start adding together. So if I take 3 of these and hook them in series, I'm going to lose about 2.1 volts through them, but I can now block 3,000 volts. And like I said, 250 volts, that number 4 galvanized line, I don't know, I think they was bringing 440 in and running the cranes on 250 volts. And the rectifier banks just had a bunch of them in series with each other. So what would be the peak voltage on 440 volts? So it'd be 440 divided by 0.707. So the peak voltage would be 622 volts. So I wouldn't use this, but I could use 2 of them, right? So guys, that's pretty much, well, data sheets. Diode data sheets are pretty easy to understand, and these things are free. Like I said, normally if I want a data sheet, I'll go to Jamico's website and just type in the part number and hit search. It'll pop it up, and you'll look down in the left-hand side. There's a little thing that says data sheets, or spec sheets, I think that's what they call it, specification sheets. And you pop that, it'll be a PDF version of it. If you want to keep it, you can right-click on it and download it, and they got tons of data sheets up on that site. Like I said, I need to find our data sheet. We got a Motorola data sheet, a data book that covers the diodes and the transistors that Motorola makes, and that book's that big. And you can't hardly get that data books anymore. Why? Because they give them away free on the internet. So any questions, guys? So bring your meter. When?
Today.
Yeah, today. Bring your meter Monday. And not for this class.
Okay.
Not for this class. In fact, this class, what category meter can we use in this class?
Less than 52.
We use Cat 1. Yeah.
No PPE.
With no PPE, but we're gonna wear safety glasses. So to PPE we're gonna wear in this class is safety glasses because solid state devices we call it POP for a reason.
But I'm still having a hard time finding wire.
Me too.
The solid strand wire. I'll put out a junk box of wire that we'll try to use. We used to have them stock it in the bookstore, and we asked them to stock it in the bookstore.
I asked him the other day, "You ever find one?"
That's every semester. That's been for the last week.
Yeah. So all I can say is I'm sorry about that, guys.
Maybe.
People sell it, but it's strange.
Yeah, can't have stranded wire because stranded. See, what we're going to do is we're going to insert these wires down in the breadboard. And if you got stranded wire, you try to insert them in the breadboard, they're going to birdcage on them. 24 gauge would work, but you'd have problems keeping them in there. So what would happen if you accidentally, they'll pop out all the time. You don't take, you get your meter lead in there, you'll come up here, you'll pull it up and pick one of them, it'll pull right out.
Or you can have a soldering class.
Solder the tips, yeah. That's what we've done on these. That's what we've done on the transformers. By the way, we put a thin coat of solder on there, thin coat. That's one of the transformer plates. But it still is. You probably need a pair of needle nose pliers. But yeah, I think we got a box of scrap wire around here. Like I said, I understand that. Normally, what we do. If we specify that wire, and they usually get it in DC, and then that's it. We put it on every other class because we don't teach these fast in sequence. But a 24-foot row will take you all the way through this stuff. You can get telephone wire. A lot of your telephone wire is solid strand, not telephone wire. Burglar alarm wire. You can buy that at Lowe's, but it's going to be 24 gauge. Huh? Somebody appreciated it. No, they don't. Yeah, 14 solid. You can't use that. That's big wire.
Did you check the price on the meter over there?
Jamco's got a lot of good meters. In this class, it depends. When you take motor controls, you're going to have a Cat 3 meter. Huh? No, you need a Cat 3 meter. It's on the cross. It'll be on the meter called Category 3. Cat 3. You need a Category 3 meter. Motor controls. This class we could use a Category 1 meter. So meters are not going to blow up in it. And we're running through, I think, three transformers before we get here. So even lightning strikes this building, it wouldn't cause any problem. Well, the guy from Snap-on came in. He wanted to sell them, and we picked it out. He was going to go to the bookstore and tell them to start stocking it for the meter. But undoubtedly, there's been some type of miscommunication somewhere.